Hello, good afternoon, and welcome to Hatch webinar. My name is Rajiv Goyal. I'm the Director of Water Solutions at Hatch. I have my colleague Spencer Snolling sitting in with me. And today we'll be talking about modeling of greenhouse gas emissions and carbon footprint analysis with GPSX. So just a few logistical things. If you have any questions on the content of the webinar, just feel free to type those in the chat box or in the questions box actually. And at the end of the webinar, we'll try to answer some of these questions. And if we cannot get to you about your questions, we will try to email you the answers or contact you through email and try to have a conversation with you. So thank you again for joining us. And I would like to start with basically, some of the introduction about the importance of greenhouse gas emissions in present day situations. We all know that we are in a climate crisis, and there is a real urgency to control and reduce carbon emissions from all of our activities. So according to 2016 Paris Agreement, there is a real urgency actually to keep the temperatures within the 2 degrees C increase above the pre-industrial levels, and even possibly reduce it to 1.5 degrees C so that we can have a sustainable future, basically. So based on these outcomes, there is a real urgency to actually tackle the greenhouse gas reductions and try to achieve carbon neutrality by the 2050. So there are many countries who are developing climate action plans, and there are many business sectors. Every business sector actually is mandated to try to develop climate action plans so that they can effectively tackle the greenhouse gas reductions and achieve those targets. So one of the really a bright example is the UK water sector, who has come out with a net zero carbon emissions by 2030. Quite an ambitious plan here, but I believe this is what is required to address this really an urgent issue. We are seeing more and more, even in North America, there are a lot of water utilities who are trying to develop climate action plans and trying to reduce the emissions so that these goals can be met in future. So with that, basically, if we look at the water sector greenhouse gases, we can see that the water cycle basically starts from, it's not only the wastewater treatment plants, but it starts with the water intake. We have the water treatment plants and water distribution systems, and the water then gets converted into wastewater, flows into the wastewater treatment plants. And, there are biosolids that are being produced, and also the treated water that is returned back to the water bodies. So during the whole water cycle, we can see that there is a lot of places where we do have a lot of energy consumption elements, but at the same time, when we look at the wastewater treatment plant itself, so in addition to the energy consumption, we also see that there are many process emissions which fall into the scope 1 emissions. This is a really a snapshot of the UK water sector greenhouse gas emissions that was prepared in 2018-19. So if we look at it, basically, they have quantified the greenhouse gas emissions from the water sector from different parts. So this part is the drinking water here on the wastewater side, and some of the credits that are being generated by green purchase of the electricity or the renewable energy production are shown here. So if we look at it very closely, then the wastewater part is almost about 50% of the total emissions that are being estimated here. And out of these, if we look at, then there are about 50% of the wastewater emissions are actually the process emissions that are being estimated as methane emissions or the N2O emissions. So this is a really one of the important aspects when we are dealing with the emissions that are coming from the wastewater facilities. So it's not only by the consumption of electricity, but there are process emissions that actually can contribute to the greenhouse gases. And this actually provides us quite a lot of opportunities, some potential opportunities that we can actually apply at wastewater treatment plants and try to really reduce the greenhouse gas emissions. Some of these opportunities are with respect to operational energy efficiencies that we can achieve in the equipments that are being used. Also, development of new technologies. We all know there are many different biological processes that are being developed, and some of these actually present some new innovations that can help us to reduce some of the nitrogen emissions, for example, or the methane emissions. Also, there are digital solutions, for example, using advanced controllers, optimizers, maybe real-time energy management systems that can be applied at the wastewater treatment plant facilities to reduce the impact, reduce the amount of greenhouse gases. The other two parts are also really interesting areas where we can look at the biogas, basically using the recovery of the biogas, using it for producing electricity, also application of solar and wind, basically at the wastewater treatment plant. And the other aspect is the carbon sequestration, which is typically trying to use either the algal reactors or trying to do some resource recovery with respect to biofuel. So there are a number of potential opportunities, and the challenge typically that we face is how do we evaluate the impact of any of these technologies in a meaningful manner. Which brings us to the fact that there is a good amount of uncertainty with respect to the emissions that take place at the wastewater treatment plants. So we know that there are process emissions, there are carbon and nitrogen transformations that are taking place at the wastewater treatment plant, which are actually producing methane gas or the N2O. There are energy inputs and some chemical consumptions that are taking place, and they all contribute to carbon footprint. And the magnitude of these emissions is actually quite dependent on the technology that we are using in our plant. For example, just a BOD removal system versus nitrification, denitrification system, or the BioP system. They have their own impact on how much either energy or how much emissions they will produce, and all of these are really technology dependent. Also, there are situations where the plant operating parameters like temperature, pH, the dissolved oxygen concentrations, etc., could also make a significant impact on the emissions that can take place at the wastewater treatment plants. The other things are, of course, the energy recovery options that we are using, the energy sources, the mix of energy, basically. And one important aspect that I want to highlight is that when we are talking about the energy sources like electricity, for example, every region has, during the day of the time of the day, basically the mix of that energy is changing. And actually, there could be different emission factors that could be attached to that electricity that is being produced. And there are actually, there is real-time information that is available with respect to the potential footprint of the energy that is being consumed at the plant. So it's changing on an hour-to-hour basis, and that could also affect the emissions that take place at the plant. But however, when we look at the quantification approaches that we have, the typical approaches that typically are being used is Intergovernmental Panel on Climate Change. So there is a report and there are some guidelines that are being provided basically with respect to estimation of the greenhouse gases from the plants, and also some of the local government operational protocols that are being developed in the US, for example, and even in some other countries, there are some regional protocols that can be used to evaluate the footprints. So these approaches typically are based on emission factor-based approaches. So there are, for example, some specific emission factors that are dictated for a certain kind of a plant, and those are being used to estimate very high-level estimation of the carbon footprints or the emissions from a plant. So this is really a top-down approach where you know, for example, your flow rates, and then you apply the the loadings, and then you apply these factors, and then you come to a number. But we have to remember that these are not really plant-specific approaches, and they are really at a macro scale. So they don't really look into any of the operational practices. They do not really look into any of the treatment technologies. So they are kind of not really as much representative, and they cannot also provide us any answers with respect to what and how we can mitigate the emissions from our treatment plants. So these are some of the challenges, and we believe the modeling basically can provide a good answer to these kind of questions. And we know that the process models are there. Basically, they have been in use for the plant design and optimization for a long period of time, and they essentially contain a large amount of information that we could use to actually estimate the greenhouse gas potential from each one of these plants. So these are really the plant-specific, they are technology-specific, they are operation-specific footprints that we can get, and we can use these models to really evaluate what would be the effect of, for example, a technological change or an operational change, what kind of changes we can expect with respect to the greenhouse gas emissions. So in our opinion, the modeling can provide a common framework to evaluate the effectiveness of operational and technological changes in reducing carbon footprint for the water and wastewater treatment facilities here. So I'm going to now get into a little bit about what we have in GPSX, just to give you an idea how you can use GPSX to model the greenhouse gas emissions in for a given wastewater treatment plant. So we developed this greenhouse gas model, which is implemented in GPSX quite a while ago, actually, and it has been there for quite some time, and it is a standard feature. It's a standard library that comes along with GPSX that you could use for this particular purpose. And some of the key points basically of this particular model. So there is a specific model called Mantis 3 model, and we are calling it like carbon footprint model, which does everything that our standard Mantis 2 model does, but at the same time it also has some additional things or additional modules that can help us in estimation of the greenhouse gases from the wastewater treatment plant. So here, I guess some of the key points that I would like to highlight is that we have broken down the greenhouse gas model so that we can evaluate scope 1, scope 2, and scope 3 emissions from these facilities. And one of the challenges, I believe, that we had in formulating this model was to actually put in the models that can calculate the N2O production, because our standard models that are there, they are just simple nitrification, denitrification processes where we look at the transformation of ammonia to nitrite and nitrate, but we don't really estimate the N2O production. So that is one of the changes that we have in this particular model. Then the other change that we have is that in the anaerobic digestion process, we are looking at the options of biogas production and also different routes for its uses, basically. So we can use it for either flaring, we can use it for in the boilers, or we can use it for energy recovery. In addition to that, there are energy consumption models, which are actually standard part of our other libraries as well. But these are already built in, so we can estimate how much energy is being consumed as part of, for example, pumping or as part of the blower blower for aerations. Some of the other factors that we have is we have the regional electricity emission factors. So for a given for electricity that is being utilized, we could use the E-grade emission factors that come from various parts in North America. But the user can also specify their own emission factors associated with the electricity uses for a certain geographical reason. In addition, we have fuel emission factors. So we are consuming some fuels for within the wastewater treatment plants, we can convert that into the carbon equivalent carbon emission. And of course, one of the strengths of this platform or the GPSX platform is that we do have a large number of treatment technologies like suspended growth and the biofilm technologies that we can use to compare and see how those changes would lead to the change in the carbon footprint estimation. So just to give you an overview of how we are doing it in GPSX. So we are calculating the total greenhouse gas emission for a given process flow diagram that you will build in GPSX. And it will be divided into 3 categories: scope 1, scope 2, and scope 3. Within the scope 1, we are calculating basically the gases like CO2 production, the methane production, and N2O production from different biological processes. So we are estimating it. So we have the underlying biological oxidation processes that can be used to estimate the CO2, N2O, and CH4 production from each of the biological processes. In the second scope, we are looking at the pumping energy, the blower energy, the miscellaneous energy, and the fuel consumption. So these are some of the energy consumptions that take place at the wastewater treatment plant, and these are quantified and then converted into equivalent carbon dioxide emissions. The third part is the material emissions, where we use the chemical uses, for example, or the material use, and the transportation. So we have implemented this for some of the unit processes that are there in GPSX, and they are typically a smaller part of the scope 1 and the scope 2 emissions, but they can also be quantified in GPSX. So to do all of this, basically what we need to do is we need to look at how are we going to quantify the gaseous emission from the processes. The other one is how we are quantifying the energy and how we are doing it for the material emissions, material-based emissions. Just to show you, basically, this is very standard diagrams, and this is nothing new, but we do have the biological oxidation processes in GPSX, where an organic substrate can be either oxidized aerobically, in which case it's going to produce CO2, or it can be, it can be oxidized under anaerobic condition, in which case it is going to produce CH4 and CO2. And from the gas liquid, the gases are basically stripped out, and they are put into the gaseous phase, and we quantify what is that gaseous emissions coming out from the biological reactors. So this is quite a simple scheme here. And the other part is basically, which is somewhat unique, I guess, to the Mantis 3 library, is the N2O production during denitrification here. So we have used a 4-step denitrification scheme here, where we are converting nitrate to nitrite, nitrogen, nitrite, and then the nitrous oxide, which we are stripping from the liquid to the gaseous phase. Also, there is a consensus in the literature and in the scientific community that there is an N2O production that takes place during autotrophic nitrification as well. So we have used some of the published models, and based on those models, we actually have the kinetics that basically utilize the ammonia and the nitrite, and through that route, it can produce the N2O basically in the system, and that gets then stripped out. So essentially, the model takes into account the nitrous oxide production during nitrification and denitrification as well. The other part is the energy emissions, and in this case, we are estimating the pumping power that is required. So these are very standard models that you will find in any mechanical engineering handbook, and the power for the blowers, and we also allow you to specify any other miscellaneous power sources that might be there. So this allows us to estimate the total power consumption that is required at the plant. And then we use that power consumption and then multiply or convert that into an equivalent carbon emission from consumption of the electricity. So in this case, what we are doing is we use the energy, the power consumption multiplied by a factor, which is a electricity intensity factor. So there is a CO2 intensity per kilowatt hour, or CH4 intensity per kilowatt hour, and the nitrous acid per kilowatt hour here. So that factor is then used, and then we also multiply it by the conversion factor for methane to CO2, basically, or the nitrous oxide to the CO2. And once we do this summation of different gases and convert them into the CO2, that becomes our scope 2 emission here. So this is kind of very high level overview of how we do it in GPSX with respect to quantification of the greenhouse gas emission from the wastewater treatment plant. One other thing that I want to mention here is that when we look at this organic substrate that is coming in, and we say that this is going to get converted into under aerobic condition to CO2 or the methane gas. So in this situation, essentially, one other factor that needs to be considered is whether this organic substrate is biogenic versus non-biogenic. So typically at a municipal wastewater, we assume that this is a biogenic source of carbon, and therefore this carbon that is being produced, actually, even though we quantify it in GPSX, we also provide an offset or a credit for this particular biogenic carbon. So essentially, we estimate the amount, but then we provide the same amount of credit so that the net emission, carbon emission from an organic substrate that is of biogenic nature is zero, basically. So essentially, if our carbon that is coming in is biogenic in nature, then we can almost neglect this CO2 that is being produced due to biological oxidation. But however, since the methane gas is 25 times or 28 times basically of, or it has a higher intensity, so any methane that is being generated is actually, even though it could be of biogenic nature, it could still be contributing to the carbon emissions, and we need to check that out. So that's one important factor. And the other factor is that we have implemented several energy recovery offsets. So we could actually use the gases that are being produced. We can take it to flare, or we can basically take it for the boiler, and we can produce some heat that can be used for heating the digesters, reducing the fuel demand for heating digesters, which can be used as a carbon offset. And the other part is the CHP, basically, where we are producing both heat and electricity. So when we are producing electricity, we can actually have a reasonable amount of credits or offsets that can actually make the carbon footprint of an aerobic digester actually almost zero or even negative. So we are going to show you some of those examples here. So I will just now jump into a desktop demonstration and show you how you can use GPSX for developing your layouts and do this kind of studies. So let me just open up this one here. So if you are a user of GPSX, then you might be familiar with this interface. So first of all, let's look at the libraries here, and we can look at, there is a carbon footprint library. So if you have a GPSX license, if you click on library, you should be able to see this carbon footprint, carbon, nitrogen, pH, 93 library here. So we click on this, then it changes to carbon footprint library here. And before I show you a layout, I would like to show you some of the global settings that we have in this particular platform. So if you right click on the system here and go to input parameters, you can see there is a carbon footprint, additional menu items that we have. And these are the places where we are going to make some global settings for setting our carbon footprint model. So some of the information that we need is basically what are the CO2 equivalents for methane gas and nitrous oxide. And of course, I mean, these factors have been taken from IPCC, but depending on the time horizon that you're looking at, sometimes these values are somewhat different. So you can actually come in here and then change those values as according to the requirement that you have. The second part that we have is basically the greenhouse gas emission factors for the electricity. So for these factors, we collected from EPA EPA e-grid factors. But of course, these factors keep on changing all the time. So it's possible that the values that we have in the database might be a little bit different than what are the new values, but you have the option to actually change those values. And this one, if you're working in a specific region, then you can actually come here and you can select any of the US regions or the Canadian region, or if this does not fit into the geographical area that you're lying in, then you can choose something different here. And also, you have the opportunity to actually come and change these values based on the latest information that you might have from your region. So it's very easy. And again, I would like to say that these values are right now they look like a single value. But as I said, if you have these values changing in a dynamic fashion, then you can actually feed in that dynamic information into GPSX and then see how the overall effect on your carbon emission is. So this is the place where you will come and change all of those stuff. The other part is basically with respect to setting up whether your carbon is coming from non-fossil or the fossil carbon. And typically for municipal wastewater treatment plants, we take that this is all coming from a non-fossil or it's a biogenic carbon. So that's why we are putting 100%, which means that what it is going to do in the system is that it's going to take away all the carbon dioxide emissions that are being produced in the biological reactors. The other part is the calorific values, which we use to estimate how much fuel consumption will be required. And then some of the fuel emission factors, like what is the CO2 equivalent of those fuels. So we have all of this information here, which you can use as it is, or you can also modify it depending on the needs that you have. This is the first step or the first place that where you will come and change your global settings. So the next thing is, let's look at a layout here, basically. And I have a layout that we prepared for this particular webinar. Here, I'm going to show you this is a MLE process. So we have primary clarifier, an oxy tank, an aerobic tank, a secondary clarifier, and the sludges from the primary clarifier and the secondary clarifier are being diverted to a thickener. And then they're going to a digester. We dewater it, bring back all the recycle lines, and then dispose of the sludge. In this particular case, there is not a huge amount of setting that we need to do to make it a to estimate the greenhouse gas emissions. But there are some additional settings that we may want to put attention to. So first of all, if I am in the aerobic tank, for example, I can look at here. There is what is going to affect here is basically some of the items that we have in the operating cost menu, in which we say what are the efficiencies of our blowers, for example, or our pumps. And for example, in this case, there is internal recycle pump. And what are the other miscellaneous sources of energy consumption? So we would like to you to take a look at it and set it up so that we have the right efficiencies of the equipments that we are using. And then based on those efficiency factors, it's going to estimate the energy consumption that we expect to take place in this particular unit process, and then convert it to equivalent carbon dioxide emissions. On the other side, if we look at the digester, one of the important changes that you could make is with respect to the energy recovery options here. So in this case, We have, for example, how much methane we are going to take it to the boiler, how much is the efficiency of the boiler, whether we are taking it to CHP, and if we are going to take it to CHP, what is the ratio of the heat recovery, and how much electricity we can achieve. So all those factors we can set it up here. Also, there are some other options where we are saying whether it is released to the atmosphere, which is typically not the case. Either we flare it, but if there is a, if there are no really good measures at the plant and you basically, if there is a leakage in your digester and the gases are just going out into the atmosphere, in those situations, it is likely that some of the gases might get into the atmosphere without actually being flared. So those are some options that you could look at here, and you can set them up basically. The other part is basically for the transport truck here, we do have some models, which are the carbon footprint models, where we are actually looking at how much fuel consumption will take place if you were to make some round trip from, take the sludge from here, haul the sludge and take it to the landfill facility, how much fuel consumption will take place, and what will be the equivalent carbon footprint of that. So those kind of things are included here. And if we were to have a chemical unit process here, then we would also estimate the associated carbon with that chemical feed, and we could include that in our layout. So those are some of the settings that we typically need to run the greenhouse gas model here. And I'll just show you a few simulations that we have done here. And for example, this is a greenhouse gas estimation for this particular plant. We are estimating scope 1 emissions. There are offsets, and this is a net emission here, scope 1. There are scope 2 emissions, scope 2 offsets, and the net scope 2 emissions, and some of the scope 3 emissions here, and the total emission, total offsets, and the net total emissions. So we have different scenarios here. So in this scenario, what we are doing is we are looking at, for example, if we were to release all the methane gas from here, what would be the footprint basically, which is of course not a typical situation, but it's just a hypothetical scenario. And sometimes maybe a valid scenario if we are taking this sludge and disposing of, for example, in the landfill where most of this will get converted into a methane. And if these are not managed landfills, then that methane actually get into the atmosphere. So what happens when we actually take all of that sludge and then release all of that methane? So if I were to just run a very simple simulation here, it's a steady state simulation, we'll see that the emissions that we are calculating is about 1,154 tons of carbon dioxide emission equivalent per year. And if we look at the makeup of this, basically, then quite a lot of this is being produced in the aeration tank, and we will look at it how this is coming. So there is a menu here which is called carbon footprint. So we can look at each and every unit process and try to identify what are the sources of emissions here. So in this case, like I said, this is a scope 1 CO2 emission. So this is 295 here. And there is not much methane we expect to be produced here because this is mostly aerobic and anoxic, but there is a small amount of methane that we are seeing here. Also, the N2O production is taking place, which is contributing a large amount. So if we look at the scope 1 emission, total emission of the scope 1 is 632, out of which there is CO2, which is 295. But since this is biogenic carbon, we take the offset for 295 here. And that's why the net carbon footprint that comes out for the scope 1 is generally contributed mostly by the N2O here. So that is what happens for the biological reactor. And for the anaerobic digester, if you were to look at what is the carbon footprint makeup here, then we will see that quite a lot of this is coming from the methane gas itself that is being released into the atmosphere. There is some offset that we are taking with respect to the biogenic carbon here, but it's not. It does not really lead to a huge offset. So there is still a large amount of methane gas that is being released and contributing to a large amount of emissions here. So that's kind of analysis that you can do. And then, of course, if I were to just say, okay, if I just improve this and flare all the methane that is being produced, what will happen? So this is a second scenario where we are actually going to take all of that methane and actually flare it, which means that all the methane is going to get converted into CO2, and we can actually, reduce the overall emissions that is taking place from this. So immediately you see that methane gas that we were releasing that was contributing around 700 tons of CO2 emission, that has now got reduced to 495 here. So this means it has a huge impact just actually even producing methane gas and flaring it rather than just letting it go into the atmosphere. So that is kind of the thing, and we can also look at what happens when we take it to a boiler, for example. So in this case, if we take it to the boiler, then in this case, essentially what happens is we could offset some of the fuel consumption that was taken for heating the digester, but it's not a huge significant amount, but it does reduce the carbon footprint by a little bit more here. But if I go, for example, and try to look at a scenario where I'm implementing a CHP scenario, and if I run the model, then I would see that, I have reduced it by another 100 tons of CO2, basically. And this happens because now I'm producing electricity. And if I were to look at the footprint of digester itself, then I would see that my actual footprint for the digester is actually negative, which means that I'm actually producing electricity and taking an equivalent credit for that. And then that is leading me to actually reduce my carbon emissions from the plant. But there is a certain amount of emission that is unavoidable and which is actually coming out from the N2O production from this nitrification, denitrification system. Just to wind it up, I guess one more simulation I would like to show you is about the dynamic nature of, let's say, if, for example, your CO2 intensity for the electricity that we are using at this plant is changing hour to hour, then how can we do that in GPSX? So we could actually create that file or a data file. We can read it from a data file, the carbon intensity for the electricity that is being used here. And then we can run the simulation here, and we can see that if this is the carbon intensity for the first few hours, and if it just changes, then of course it will have the effect on the emissions that are basically happening at the plant. So this, I believe, is a really a useful tool in situations where we have variable carbon intensity associated to the electricity that is being drawn from the grid. And it could potentially offer some benefits with respect to, for example, real-time management of our facilities, where we can run our facilities in such a way that we can actually reduce the peak demand, not only the price, but also bring in the carbon as an objective in our optimization of these facilities. So these are some of the things that we could do with the GPSX simulation platform. So now coming back to our slides here one more time, I'll very quickly run through a few desktop studies that we have done and show you essentially, just a study that we did just to show you what could you achieve with GPSX. So in this case, of course, we want to compare apples to apples, and sometimes it's not really possible if we don't have a good tool. So in this case, what we try to do is it's always a question in everybody's mind: how effective are BNR processes, and what could be the change in the carbon footprint when we go from carbon removal to, let's say, nitrification, or if we go for denitrification, remove the nitrogen, or if we go for biological phosphorus removal systems. So all those questions we can evaluate those different kind of configurations and try to see what could be the impact? What are the factors that we need to take into account while planning, designing, or operating these facilities? The second question that comes to our mind is, of course, when we are developing new technologies, how are these technologies? Are they carbon effective? Can they contribute to the goals of carbon reduction, basically? And all of these things, the modeling platforms can provide a good, platform for evaluating those kind of things, apple to apple, because then we can compare them to achieve the same treatment objectives and try to see how these different technologies are going to behave. And the third group is, of course, valid for different type of biogas recovery options. We could even enhance it further to include maybe other resource recovery facilities, resource recovery technologies that can be then used for generating more carbon credits at the wastewater treatment plant facilities. But in this case, I would just show you, this is a group 1 where we studied some BNR processes, and the group 2 where we compared a couple of few technologies here, and the group 3 where we looked at different energy recovery options. So just some assumptions. We basically had the battery limit around the wastewater treatment plant itself. The carbon in the wastewater was considered to be biogenic in nature. And then we didn't really include, the electricity consumption that takes place in the utility buildings, in air conditioning or so those kind of things were not included basically in the calculations here. Also, we assumed the carbon equivalent for electricity based on the US national average that I just showed you. And also we used the default nitrous oxide production kinetics in GPSX model to actually look at that stuff. And one other thing is that we didn't really include the nutrient recycle from solid treatment processes while comparing, those different configurations in group 1 and group 2. So just a very high level here. So here on the bottom, you can see there are various different configurations. The first configuration is carbon removal, where we have no nitrification, which means that we are running the system at a very low SRT, and there is no primary clarifier. The second one is carbon removal and with nitrification, and there is no primary clarifier here. And in this case, the third one is carbon removal and nitrification with primary clarifier. And the fourth process that we looked at is the carbon nitrification and denitrification. And then, of course, going to BioP and another BioP where there are stricter requirements for the affluent limits. And this is with adding extra carbon, external carbon source. So as we can see, like this, we can concentrate on this net emissions here. We can see that if we are just doing a very simple carbon removal process, we are not actually going to generate any nitrous oxide in the plant within the boundaries of the wastewater treatment plant. And our energy consumption with respect to aeration are also very limited. So actually it produces a very low amount of carbon footprint. But if we were to go for nitrification, then we actually start to produce nitrous oxide, and that actually increases the footprint. We also need to run our system at a higher SRT, and that increases our aeration demand as well. So as we go here, then in this case, this reduces because we are removing part of the nitrogen in the primary clarifier, and we are also removing part of the carbon. Actually having a primary clarifier and diverting all of that carbon to anaerobic digester could actually provide a good benefit. So now if we go for nitrification, denitrification, then we also see a little bit of increase, because during denitrification, there is some additional nitrous oxide that is being produced. And then we go to BioP plants, 4-stage plants. And here, I guess we gain some benefits with respect to aeration itself. But when we start to add more carbon into the system to achieve higher denitrification and BioP, then we start to lose that advantage, and our carbon footprint starts to go up. So by the way, these numbers are just numbers which are represented as kilograms CO2 per meter cube of wastewater that is treated. So again, looking at what makes up of these emissions, here we say that net scope 1 emissions. So this is mostly energy consumption here. When we go for nitrification, then there are process emissions which contribute a large amount of this. The energy consumption, not as much. So we can see that the energy consumption stays quite similar throughout the system. And in fact, for denitrification system, since we are using nitrate as an electron acceptor, reducing our oxygen requirement, we actually gain some additional value there. But at the same time, there are some process emissions which are actually much higher. And if we start adding carbon, then that itself starts to contribute to the overall carbon footprint for these facilities. And this is very interesting. Actually, here we try to compare our traditional MLE configuration versus MABR, which is a membrane-aerated bioreactor, a new technology that is being introduced in the marketplace, and the MABR, which is a moving bed bioreactor system. And we looked at the carbon footprint here, and surprisingly, it appears that the MABR system could be quite effective actually in reducing the overall emission from the processes, which means that, first of all, they are more energy efficient. And the second thing is the nitrous oxide production from this system seems to be much more controlled or limited than the other systems like MABR. And it is a little bit curious. Probably there is more research that is needed here, but there are experimental studies actually that alludes to the same phenomena here. And we believe that this is probably because of the nature of the biofilm that grows at the MABR and MABR. Also, the dynamics of the profiles of DO, ammonia concentration, nitrite profile, and some of the mass transfer of N2O from the bulk that takes place in this system. So there are a lot of things that are playing into these systems, but it appears that MABR system could be much more effective in reducing the carbon emissions from the treatment plants there. Again, here, as I said, the process emission seems to be much lower. On the other side, the MABR seems to produce actually much more nitrous oxide, which adds to the total footprint, carbon footprint of this technology. So other thing is, this is a group 3 where we looked at some of the energy recovery options. And here, when we look at it, basically we can see that as I showed in the desktop demonstration as well, that as we go more towards the energy recovery, actually our footprint starts to keep on going down. So in this case, when we are actually passing it through the CHP, then in that case we have the lowest footprint. And the reason is basically we have some additional carbon credit for the electricity production there. So our anaerobic digester process itself actually becomes almost like carbon neutral. So those are some of the reasons that we see, for this particular phenomenon. So just to wrap it up, basically, and summarize, I do believe that there is a real urgency. We see that there is a lot of interest in the marketplace, especially in water utilities actually trying to get to the climate action plans. And there is a real urgency to reduce greenhouse gas emissions from in each business sector, actually, not only water utilities, but as a water engineer, we can actually try to, really contribute towards the water sector and try to, help achieve those goals. And one of the things that we do believe is that GPSX process models, they provide really a systematic framework to evaluate apples to apples, basically, some of the different greenhouse gas reduction options, whether you're looking at different technologies, whether you're looking at different control options or energy and energy recovery options. They provide you really a good way to actually evaluate it in a really a kind of an objective way, rather than just using some emission factors and trying to come to some kind of conclusions. The other part that I want to mention is that based on the current understanding, I do believe that the technologies that can play an important role is somehow having biological processes that do not add to N2O production, but actually can contribute to N2O reduction. Those could be really helpful technologies. The other one is, of course, energy efficient aeration, whether we are looking at, for example, improving our aeration grade, or we are looking at our biological system, or using some innovative ways of aeration that could reduce the energy, that could go a long way. The other part is carbon diversion. So the more carbon we can divert to the anaerobic digester, the more gas and the more electricity we could produce. So those kind of options are really good. And of course, the other part, which could probably be quite contrary to the expectations of nutrient removal, is the minimization of external carbon sources that we have to use. So these are some of the high-level ideas I believe that could be utilized in wastewater facilities for carbon reduction. The other aspect that is quite interesting and I believe could be really useful is the potential application in real-time plant operational optimization. So the example that I showed, where if we have a pre-knowledge of the future energy composition and using that energy consumption, trying to really, run our plant so that we can try to bring down the peak or reduce the peak at the plant, and try to, take advantage of those fluctuating energy mixes that we are utilizing at our plants. So those are some of the items or beliefs or some of the outcomes of this this study, and I hope that you kind of get something out of it and understand how you can use GPSX basically for evaluating carbon footprints for your facilities. So with that, I would just stop here and pass it on to Spencer to give you some updates on what's going on at Hatch.